Thank you, Justin, for accepting my invitation, like the rest of the speakers. Justin is an assistant professor at the university at Albany, SUNY, and he's going to tell us interesting stuff about counting problems in persistent and enriched topological summaries. And hopefully this will not go away without mentioning sheaves.
Yeah,
Over to you.
I might let you down a little bit in that regard. Yeah, and thank you, Aras, for inviting me. And I also want to apologize to everyone in on this Zoom meeting that this will be the first talk where there's not actual real data, just mostly cartoons, either drawn in PowerPoint or drawn by hand. I think we often need the idea first before we can always apply it. So this is sort of a string of developments that is in progress. So, all right, so, oops, that's not exactly the order I wanted to show. So let me do this. I realize I'm in Tech Shop, not the other one. Bear with me. All right, I minimized the wrong one. There we go. All right, so apologies for that quick delay. And I also want to encourage everyone to stick around and for Hans Ries's talk, who is going to be speaking right after me. In fact, some of the initial ideas of considering these inverse problems in a simple geometric setting emerged out of discussions with Hans when he was an undergrad at Duke, and he considered problems related to curvature as well back in 2016. And so I want to give my sort of big picture for this talk, which is sort of summarized via the language of a pipeline. And the subject of today's talk is going to be inverse problems in topological data analysis. And what this essentially means is I'm asking the question, to what extent can we reconstruct a data set from its barcode or persistence diagram? And the point I want to make here is that sometimes by enriching our topological summaries, whether they're, say, merge trees, which keeps track of components as you filter a space, or Reeb graphs, which keep track of sort of connected components of scalar valued data, or you look at a single fiber or level set. If you enrich each of these, there's settings in which you can actually count equivalence classes of data sets that have the same barcode. And the sort of goal here is that we want to classify so that we can disambiguate. And so the pipeline sort of starts with data on the left, which sort of fibers continuously over a persistence diagram, meaning that you could take whole rigid motions of data, for example, and produce the same barcode. But sometimes standing upstream from this barcode, there are other topological summaries which refine. And then by enriching these topological summaries, we get even more information about our data set. And the goal is to do this in sort of a discrete way that's still computable. And just to prove to you all that inverse problems isn't something that I'm just interested in. I think one of the first really impressive bits of work goes back to Yasu Hirooka's group in Kyoto, where he was considering the problem of, suppose you take a point cloud, you compute its persistence diagram. Now imagine you consider a nearby persistence diagram. Is there a way of flowing the point cloud over to the new persistence diagram? And many other people have considered similar variations on these sorts of inverse problems. As was already mentioned earlier today in Liz's talk, I have work with Cheyenne Mukherjee and Catherine Turner on to what extent, well, just by studying Euler characteristic in a certain number of directions, does that determine the shape? And then there are sort of variations on this considered by Steve Udo. And then some of the ideas I'm going to be talking about today started in discussion with a larger group of people at the Institute for Mathematics and its Applications. And it's been given the title of Moduli Spaces and Morse Functions for Persistence. And that was recently published in JACT. And then the main result of today is going to be counting embedded spheres with the same persistence. And this is in preparation with my PhD student, Jordan Deshay. All right, so as a quick review, when we're trying to do the study of just components and not homology, often the object of study is a function on some domain. So you could think of this as a intensity of a image where you've got some value between 0 and 255, for example. And you want to imagine what happens if you look at all points which have a given intensity or less. So that's a sublevel set. And if you consider something that includes from lower intensity to higher intensity, you're going to get a proper inclusion of sets. But if you were to study something like connected components, that doesn't necessarily mean the map on components is injective. So here, if I consider my prototypical water filling example, I've got sort of 2 puddles of water at this level. And then as I hit another local minimum, I reach another puddle. But then when I reach my first mountain pass, my first local maximum, those 2 puddles merge. And whoops, sorry, I accidentally scrolled too fast. Well, you're now seeing my talk entirely in high speed. Right. And of course, I've got it all inverted, so this is complicated. Sorry, I will not touch my mouse. This is the sort of cartoon which you're seeing with just looking at components. And of course, an easy way of summarizing all this is using something called the merge tree, which I don't think has really been discussed today. It was alluded to in Liz's talk, which is you have a tree-like summary of how connected components evolve with respect to a filtration. Here you have a leaf node for every local minimum, and then you have an internal node for every local maximum. So people haven't really gotten into the underlying mathematics behind how persistence diagrams or barcodes arise. So let me tell you a little bit about that. So the prototypical rule, at least for studying H0 persistence, is you want to look at what's called the Eldar rule. So if I have this merge tree, I'm going to imagine I'm sweeping from bottom to top. So it's from -infinity to +infinity. And whenever you encounter a leaf node, you're going to start drawing an interval. This is going to be a bar in your barcode. And whenever 2 branches meet, you can't keep drawing both intervals because now it's a single thing. And the rule is that the one that was born earlier persists, and then you have to stop drawing the younger one. So picture's worth 1,000 words. So if I have the same function I just considered, to the left, it's graph. In the middle, it's merge tree, and it's barcode to the right. As I step through, I hit my first leaf node, I start drawing an interval. Then I reach my next leaf node, I start drawing another interval, another bar in the barcode. And then I reach another leaf node, minimum, another bar. And then finally at my first internal node, I have to stop drawing the interval that was drawn later, the younger one, as the older one survives. And then similarly here, the essential class, the one that was born earliest and first, keeps going, and that goes on forever. There's no other collisions. So this is the pipeline for going from a function to a merge tree to its barcode. So the first question that I considered back in 2016, 2017, which was how many merge trees give you the same barcode? And so there's actually a pretty easy way of reconstructing merge trees from barcodes where you have to keep track of all possible choices. So one is to take that long infinite bar and make that the sort of spine or backbone. And then proceeding by later death times or earlier death times, you want to take each bar in the barcode and then ask where can I attach it in the merge tree so as not to violate the Eldar rule. Now, this is a situation where using the alternative but completely equivalent way of thinking of the barcode as the persistence diagram is very useful. So here you think of the birth time as your x coordinate and the death time as the y coordinate. So that allows you to encode each interval as a point in the persistence diagram, with the caveat that if I have no death time, I will just sort of draw that below this diagonal. And so essentially what the Eldar rule says is, it says that I have to look at intervals which are properly contain me, which corresponds to being up and to the left in the persistence diagram. And so this way of attaching could be encoded or visualized by augmenting the persistence diagram with what point gets attached to what other point. So here I've got both of my finite components, my 2 points above the diagonal, attaching to the one essential class. And that just means I attach to that one spine. Alternatively, I could have attached over here. So instead of attaching to the oldest, I attach to the second oldest component. And so this already proves to you that sometimes the same persistence diagram can be achieved by 2 very different merge trees. Indeed, these are actually non-isomorphic in a certain category. All right, so again, that's the difference. So if you essentially just keep track of all the possible places where I could have attached, which means I take my barcode and then I look at all the intervals that properly contain a fixed bar in the barcode, and I do that for every bar in the barcode, I get a number that's mu bij, which essentially counts the number of points up and to the left of a given point in the persistence diagram. And if I multiply these numbers across all of the points in the persistence diagram, and it doesn't really matter in what order you do it, but I like to imagine it's kind of sweeping my persistence diagram from top to bottom, you get this sort of determinant-like formula, and that counts the number of merge trees which have the same barcode. And you'll notice that it doesn't matter necessarily how many intervals there are, but rather what's the arrangement. So here are 2 barcodes that have equal numbers of intervals, but they actually have different number of redundancy. So there's a unique merge tree that encodes the barcode on the left, but there's actually 2 that sort of map to the barcode on the right. Okay, so let's try to at least connect this in spirit with data. So imagine we're now interested in, say, time series, which you can think of as just a function from the interval to R. And so the question which I want to ask is, how many different functions on the interval have the same barcode? So how lossy is this topological summary? So the first answer is obviously there's infinitely many, in fact, uncountably many. However, if we impose an equivalence relation on time series, which is called graph equivalence, which asks that I be able to sort of reparameterize my interval, reparameterize time in an orientation preserving way, and take one function to the other, that plus a sort of Dirichlet boundary condition, that actually gives rise to a finite classification of functions with the same barcode. And there's a really brilliant idea from Yuli Baryshnikov, which says, let's just take the merge tree and indicate chirality. So when I do my sort of filtration from bottom to top, you'll notice that I get intervals that are sort of born, come into existence, and then merge. But because I'm looking at intervals inside of the unit interval, I can say which one's to the left and which one's to the right. And so I just decorate my merge tree with a handedness, left or right. And this then tells me that I can actually come up with a way of representing each equivalence class using this chiral merge tree. And in fact, you can go backwards from this, as I'll indicate. So a simple modification of that earlier sort of determinant formula I gave was, let's just multiply that by 2 to the n minus 1. where you have n-1 sort of short bars or finite bars. And every time you're attaching, you decide, am I going to attach this on the left or on the right? And that's that binary decision. So apologies for the hacky hand-drawn figure, but if I take that same barcode we've been considering and I now consider this sort of chirality information, which means do I want to attach on the left or the right, I can see that I've got 8 different chiral merge trees, each of which map to the same barcode, which corresponds to the fact that there were already 2 possible merge trees realizing this barcode, and then an additional factor of 4 for each of those. So the way in which I can reconstruct a signal or a function on the interval from one of these chiral merge trees is I use what's called the in-order tree traversal in computer science. And this allows me to essentially translate all of my nodes into x coordinates, and then I just use the function values to connect up my function. And you'll see there's a natural sort of pairing or involution on the space of time series where I just take this mirror imaging. And that's one thing which persistence can't tell the difference between, is if I take a function and I completely reverse it, it has the exact same persistence. So that's interesting, but maybe not interesting enough. So let's consider possibly an application to sort of voxelated data, where we're looking at sort of spheres or sort of root systems embedded inside of R3. And we're interested in the question of just how lossy is persistence. And the fundamental example I want you to have in your mind is if I consider this level set barcode, which is the sort of combinatorial representation of zigzag persistence, which Brittany just spoke about, then I have these sort of 2 fundamentally different embedded shapes with the same level set barcode. And in fact, if I don't just care about zeroth homology, but I actually care about connected components, which is sort of set valued information, that gives rise to the Reeb graph. These 2 shapes have absolutely the same Reeb graph and barcode. I call this sort of middle sphere here the worm, and this sort of looks like a balloon where you've pressed in on side. I call that the shot glass. And I gave them these names because I came up with these examples when I got back from Mexico a few years ago. So let's go ahead and identify and say specifically the setup here. So I want to consider my objects are embedded spheres, such that when I project onto the z-axis, this is a nice Morse function. And I'm going to say that 2 of these spheres are height equivalent if there's a way of sort of transmorphing one embedding sphere into the other without raising or lowering anything. So it's a level set preserving isotopy, to use sort of fancier language. And this guarantees that if 2 spheres are height equivalent, then they're going to have identical level set barcodes. And a simple fact, which I hope to remind you all of, which is that because I've made this nice assumption, if I look at any regular value, so non-critical value of this function, which is a composition of embedding followed by projection, that's going to give me a disjoint union of circles. And if I reapply this embedding, I now get embedded circles in the plane. So let's take a typical regular value for the 2 examples. And you'll see that what distinguishes these is I've got one where the circles are sitting side by side, and then the other one is nested inside of the other. So one thing you can do is you can enrich your Reeb graph with the nesting poset, which records when is one circle inside of another for a given regular value. And so the idea is just by enriching the fibers of the Reeb graph with this nesting information, you can have further discriminatory power. No, it's still finite. Just to look at some more examples, if we take the same sort of barcodes we've been looking at, and you ask, well, how many embedded spheres realize these? well, here I can hang on the outside or stick on the inside. And now if I add another one, I keep adding on, where do I hang these sort of noses, and where do these pockets emerge? And the one thing which is very different from the one-dimensional example, looking at functions in the interval, is you can sometimes take an arm and sneak it inside of a pocket. And that causes the sort of combinatorics here to be much more different. Again, to give you sort of a real life example, imagine you think of yourself, the exterior of yourself, as a two-sphere embedded inside of R3. If you stick your hand in your back pocket and then you sort of reach behind, like you're going to do some sort of yoga bind, this is going to give you a very different height equivalence class than this one. Which in particular means the bad news is even with this height equivalence relation, there's infinitely many height equivalence classes with the same level set barcode. And you can see that just by reaching in and winding around infinitely many times, we can generate arbitrary height equivalence classes with the same barcode. So we do what we always do in math, which is just define away problems we'd rather not think about. If I say that a sphere is unbraided, we can actually count exactly how many height equivalence classes have the same barcode. But we have to introduce another bit of notation, which just kind of goes to the theme that Henry was talking about earlier, which is that the persistence diagram actually has a lot of secret information lying in it. And you need to not just think in terms of things that are like close to the diagonal or not. So in particular, if I have a barcode like this, I'm gonna let eta bij correspond to the number of intervals or points that are born earlier than I am, but then die earlier than I do. And I'll give you a visual depiction of that soon. And the result, which Jordan helped me pin down, was that if I fix a given Reeb graph, the number of unbraided height equivalence classes of spheres gives me another sort of multiplicative formula where I take this eta bij and I add 2. So just putting that together with the merge tree counting formula, I now have this really nice result that says that the number of unbraided spheres with the same barcode, which I can think of as the number of height equivalence classes, sort of sits between an exponential times the number of merge trees and a factorial times the number of merge trees. So let's quickly get a handle on why this is true. So first of all, that eta number, that's going to correspond to the number of pocketing moves. That's indicated by the number of points that are down and to the left, but also above this line. So counting the number of points in this rectangle is my eta number, and the number of points up here is my mu number. So I can mess around with the geometry of how my persistence diagram looks, and I'll get different results. So for example, this persistence diagram, I have only one merge tree, but I actually have, for that single merge tree, 24 height equivalence classes. This sort of corresponds to the fact that I think this number plus 2 plus 3 plus 4, so this ends up giving us 4 factorial. Similarly, if I want to maximize the number of merge trees, that actually minimizes the number of height equivalence classes per merge tree. And just to give you a quick sort of proof intuition for why this is true, one of the secret bits of information in persistence is if I pick a point on the diagonal and I look at points up and to the left, that tells me the homology of the level set. And so at this point, I've only got one point up to the left, which means my level set looks like a circle. Now I have 2 circles, and of course there are 2 possible arrangements. Here I have 3 circles and 6 possible arrangements. And so as I meet this 4th point, I ask, what are all the places in which I can insert the birth of a 0 handle? And so essentially taking all that and multiplying through gives me exactly the formula I came up with. So, so ongoing work is that we'd love to be able to sort of figure out ways of enriching the persistence diagram with some of this more interesting topological information like braiding between critical values, with the goal of sort of being able to describe the whole homotopy type of embedded spheres that have the same barcode. And then a big part of Jordan's thesis now is counting the number of Reeve graphs that realize a given level set barcode. And this turns out to be very, very difficult. But all of this is meant to provide mathematics that help provide a general explainable theory for understanding misclassification of data sets using TDA. And again, those are all those papers again, and I thank you for your attention.
Thank you very much, Justin. Please unmute yourself and let's clap for Justin. Any questions? Please unmute yourself and go ahead asking questions. If not, then feel free to use the chat box to send me questions.
Hi, Justin. Thanks for your talk.
Thanks.
I'd like to, I just put a link in from the material that you talked about. I think it's important to mention that a lot of this stuff comes from a group effort and goes on to some really interesting directions. I wanted to ask about the braiding that you mentioned. So I totally agree that the braiding stuff gets pretty crazy. But say you bound the number of braidings, or sort of the number of times things braid. Does that give you some? Are there some easy results from that?
Yeah. So I think the right thing to say is, in that situation, you don't necessarily need to bound the braid, but rather you sort of, I think ideally the right result would be to say something like, decorate the Reeve graph with a element of the braid group that tells you how it's wound around. And that's going to be sort of fundamentally a sort of finite result. And so, yeah, you could try to do something where there's a question of how do you reduce a given embedded sphere to a certain normal form. But that's proved to be really difficult to figure out, and I don't really have anything else I could say about that right now.
Okay, thanks.
Thank you very much. Any more questions? Maybe I will ask a question just so that people think of a question. I think in one of your slides you said, I think there was two figures of two objects, and you said they both have the same persistent barcode. Would you mind just to elaborate? I just wanted to imagine. Yes. So the previous one. Another.
Here.
No, the one where you have the two objects and you said they have the same barcode.
Yeah. Yep. Let me
Yeah, great. So I just can't imagine in my mind, maybe it's just only me, if the one at the right, because I see is there any like, so from the red dashed circle seems that this is bigger than this, the one at the right. Is that true?
Yep. Yeah. So this one here, you're sort of, it's like if you're looking at the, even like a coffee mug, for example, if I were to slice here, you would see that there's sort of a boundary circle, and then there's also a circle. And so if you just got an X-ray and you're analyzing the topology right at that level, you wouldn't be able to tell whether or not that circle was inside or whether it was outside. And what's more is that as you start to come up to that sort of lip of the cup, then you end up having this situation where the number of circles drops to a wedge of circles. So now it's a wedge where the other circle's inside, but then above it, it's very hard to sort of visualize, but if you were to slice right here, then you would get something that kind of looks like a crescent moon almost. That is topologically still a circle. So.
Great.
But these two shapes are homeomorphic anyway.
Yes, yeah, absolutely.
You can play with it and take
That's right.
either branch inside the other. This is basic topology.
Yep, yeah, exactly. But the point is, if you like try to visually look at them, they're obviously different.
Can I ask you a question about the graph equivalence?
Yep.
Merged trees?
Yeah, I think that was
not a slide. Yeah, no, the one with. Well, I mean, okay, but the slide itself. I mean, when you talk about graph equivalence,
yep.
Isn't there a possibility of defining some group actions, finite group actions on merge trees, and then you get equivalence classes, then you can use some counting?
Yep, yeah. So there's...
I mean, these coset, like whatever it is. Sorry, excuse me. I used to do these things a long time ago, but I forgot about it.
Yeah.
Some group actions on these, finite group actions.
Right, so I'm not entirely sure about the finite group actions, but there is definitely a sense where you want to imagine how you would say morph one signal to the other. And just going back up to this definition real quick, I'll note that in like dynamical systems, this actually looks a lot like a result called topological conjugacy. But the difference is that we fix the real value.
Sure.
So, because that's important to persistence, doing filtrations or looking at fibers.
I mean, if you go back to that sorry, just quick one.
Sure.
I mean, if you look at the first two,
yep,
simply a rotation.
Yep.
In the horizontal.
Yep.
Makes it equivalence.
Yeah, so there's definitely an involution on the space.
Involutions, yeah.
Yep, just by swapping left and right labels.
Sure.
Yep.
Okay.
Yeah, thank you, Saba. So there's a question from Leonid Fedorov. Thank you very much for the talk. Did I understand it correctly? The merge tree corresponds to H0 barcode. If so, is it possible to elaborate on the difficulty encountered when counting in higher homological dimensions?
Right, yeah, so just to state it clearly, the merged tree determines the H0 barcode, but not vice versa. And just because if you want to think about it, one tells you exactly what the sets look like when they attach, that's the merge tree. Whereas when you linearize and you put everything over let's say a field of coefficients, then you end up losing exactly who attaches to whom. But there's that cryptic line in the book Computational Topology by Eldar and Hare, which says that all of persistence comes from generalizing the Eldar rule to higher. The trouble is there's no sort of like nice set theoretic basis for capturing higher homology, but there is some tricks you can do, but yeah, that's something that's probably best handled offline.